Hello students, welcome to the physics class. This is electrostatics, which is the 7th presentation. In this we will be seeing about electrostatic induction and then capacitors and what are the uses of capacitor or the applications of capacitors. So the first one is electrostatic induction. Now we know that we can produce charges by rubbing and touching. By rubbing, if you remember, when a glass rod is rubbed with a silk cloth, it produces positively charged particles, and when an ebonite rod is rubbed with fur, it produces negatively charged particles. So we can produce charges by rubbing as well as by touching. But do you know we can produce charges without actual contact? Yes. Charging without actual contact is known as electrostatic induction. Now the charges which are produced are known as induced charges, and the phenomenon is known as electrostatic induction. Now these charges are used in electrostatic machines like Van de Graaff generators and capacitors. Now we'll see what are the steps involved in order to produce charges. Either it can be positively charged particles or negatively charged particles. Now here we will see how you can produce positively charged particles. For this, the first step is we have to take an uncharged metallic sphere which is kept on an insulating stand. And then you have to take a negatively charged rod and it is brought near it. Due to repulsion, the free electrons move away and pile up at the farther end and the positive charge in the nearer end. Now the sphere is grounded, then negative charge flows to the ground and the positive charge remains held. Now when the rod is removed, the positive charge spreads uniformly over the sphere, and this is how we produce positively charged particles. The diagrammatic representation of electrostatic induction is given. Now as I told you, a negatively charged rod is brought near a sphere which is spherical in shape and which is supported by insulating stand. Now what happens? Because the rod is negatively charged, the nearer end will become positively charged and the farther end will become negatively charged because like charges will repel each other. Next step, the negatively charged and that part of the sphere is grounded, so all the negative charges go to the ground or it is earthed, so it goes away, and the sphere is left with positively charged particles. Okay, and since it is spherical in shape, the charges get accumulated or gets uniformly distributed over the surface of the sphere. In the same way, we can produce negatively charged particles also. How? Instead of a negatively charged rod, if a positively charged rod is brought, then the nearer end becomes negative and the farther end becomes positive. Then the reverse action takes place. It gets earthed, so all the negative charges will get accumulated in the sphere. Next, we talk about dielectrics or insulators. Now what is a dielectric? It is a non-conducting material that has no free electrons. The electrons are bound with the atoms. Examples of dielectric are ebonite, glass and mica. Now when an external field is applied, they realign themselves in a specific manner. So they are made up of either polar or non-polar molecules. This question, polar or non-polar molecule, is an important 3-mark question. The first one is non-polar molecules. Now in a non-polar molecule, the centers of the positive and the negative charges coincide. It has no permanent dipole moment. When an external field is applied, the centers of the positive and the negative charges are separated by a small distance, which induces dipole moment in the direction of the external field. And examples for non-polar molecules are hydrogen, oxygen and carbon dioxide. If you see in the diagram, you see the center of the negative charge coincides with the center of the positive charge in a non-polar molecule. When an electric field is applied, they are separated by a small distance which constitutes a dipole moment, and it lies in the direction of the electric field. Next we come to polar molecules. In a polar molecule, the centers of the positive and the negative charges are separated. They have a permanent dipole moment. When an external field is applied, the dipoles align in the direction of the electric field. And examples of polar molecules are hydrogen, nitrogen, HCl and ammonia. Now we see diagrammatically how the polar molecules act in the absence of an electric field and in the presence of an electric field. In the absence of an electric field, they keep moving randomly. Whereas when you apply an external electric field, the molecules partially align with the field. The next concept is about polarization. It is defined as the total dipole moment per unit volume of the dielectric. For most dielectrics, the polarization is directly proportional to the strength of the external electric field. So, it is represented as Xi E A external. Next, the other concept is dielectric breakdown. When the external electric field applied to a dielectric is very large, it tears the atoms apart so that the bound charges become free charges. Then the dielectric starts to conduct electricity. This is called dielectric breakdown. This will come as a definition, dielectric breakdown. Similarly, polarization will come as a definition, 2 marks or 3 marks. So when an external electric field is applied to a dielectric is very large, it tears the atoms apart so that the bound charges become free charges. Then the dielectric starts to conduct electricity. This is called dielectric breakdown. Another definition, what is dielectric strength? The maximum electric field the dielectric can withstand before it breaks is called dielectric strength. And in the table they have given you for different substances what is the value of the dielectric strength. For example, mica, Teflon paper, air and Pyrex glass. Next we come to capacitors. Now in all your electronic instruments, for example your TV or your fridge or any electronic or radio set, anything, if you open at the back you will see small components, electronic components. One such is your capacitor. I hope you would have seen the capacitor. Now what is a capacitor? It is a device which is used to store electric charge and electric energy. Now diagrammatically they have represented capacitors. Okay. Now in this, if you see capacitors, a simple capacitor is shown over there. It consists of two parallel metal plates which are separated by a small distance. Now when the capacitor is connected to a battery of potential difference V, the electrons are transferred from one plate to the other plate by the battery, so that one plate becomes negatively charged and the other positively charged. Now the potential difference between the plate is equivalent to the battery's terminal voltage. Now if the battery voltage is increased, the amount of charges stored in the plates also increases. Or in general, we say the charge stored in the capacitor is proportional to the potential difference. That is, Q is proportional to V. Now to remove the proportionality symbol, we have to introduce a constant. The constant is nothing but C, which is known as the capacitance. Or Q is equal to C into V, or C is equal to Q by V. And this is how you represent your capacitance. So what is the definition for capacitance? Capacitance is defined as a ratio of the magnitude of charge on either of the conductor plates to the potential difference existing between the conductors. And the SI unit of capacitance is Coulomb per volt or Farad. It is named after the scientist Michael Faraday. Farad is a very large unit So practically it is measured as microfarad. That is 1 mu f is equal to 10 to the power of minus 6 farads, or picofarads. 1 pf is equal to 10 to the power of minus 12 farads. Next we have the capacitance of a parallel plate capacitor. You have two parallel plates, plus Q and minus Q, which are separated by a small distance d, and the area of cross section is taken as A. Now the electric field that is flowing across the plates is given as E. Now, if you would have remembered in our applications of Gauss law, we have studied one of the application between two parallel plates. What is the electric field at points outside and within inside the plates? That principle is used over here. We know that E is equal to sigma by epsilon naught, where sigma is equal to the total charge that is enclosed in the area, that is Q by A. Therefore, E is equal to Q by A epsilon naught. Now, we have to calculate the potential difference, because C, in order to find out the capacitance, C is equal to Q by V, or V, we have to take the formula of V as E into D. You know the value of E, just substitute that into D. Then substitute in the value of C. C is equal to Q by V, or C is equal to Q by QD by A epsilon naught. A epsilon naught goes on top, Q and Q gets cancelled. Therefore, C is equal to epsilon naught A by D. Now, the points to be noted over here is capacitance is directly proportional to the area of cross section. It is inversely proportional to the distance between the plates. Now, if A increases, capacitance also increases. If the distance D is decreased, potential difference decreases with constant E. Next, in all these cases we saw infinite plates. Now, suppose say you have a finite plate. Then what happens is, at the ends the electric field bends, and this field is known as a fringing field. Now, while deriving an expression for capacitance of the parallel plate capacitor, the expression of the electric field for finite plates is used, but for finite sized plates the electric field is not strictly uniform between the plates. At both edges the electric field is bent outwards as shown, and this is called as the fringing field. However, under the condition D squared is very much less than A, this effect can be ignored. Next, we have to calculate the energy stored in the capacitor. As you know, energy will deal with the work done. So, dW is equal to V into dQ. Now, you know what is V? C is equal to Q by V, or V is equal to Q by C. Next, work done W, integral. So, integral of, just substitute the value Q by C dQ within the limit 0 to Q. Therefore, when you integrate it, you get it as Q squared by 2C, or the potential energy is stored as Q squared by 2C. Now, substitute the value of Q, you get it as half CV squared, because we know Q is equal to C into V. Now, you know your value for parallel plate capacitors. C is equal to epsilon naught A by D, and you know the value of V, which is equal to E into D. Substitute these values, you get your UE as half epsilon naught A by D into ED the whole squared. D gets cancelled, you get it as half epsilon naught AD into E squared. A into D is nothing but your volume. Therefore, the energy stored per unit volume of space is defined as the energy density UE, which is equal to U by volume, or UE is equal to half epsilon naught E squared. Next, we'll see the applications of capacitors, where practically capacitors are being used. Now, as you see in the picture, you have a digital camera with a flashlight. So the camera flashlight uses the capacitor. Okay, the flash which comes from the camera when we take photographs is due to the energy released from the capacitor, which is called as the flash capacitor. The second application is your heart defibrillator. Now, this is used to when a person is gasping for breath, or you can say when he has a heart problem and he is not able to breathe. Usually the first aid which we give is we just put our hands together and just pump in the we keep on beating the heart. So this is almost a device which is used for that purpose. So it is a device which is used to give a sudden surge of a large amount of electrical energy to the patient's chest to retrieve the normal heart function. This also uses the capacitor. Now, the defibrillator uses a capacitor of around 175 microfarads, which is charged to a high voltage of around 2000 volts. The next one is your ignition systems in your automobiles. Now if you see in your ignition system, you have a capacitor, okay, and the ignition system of automobile is used to eliminate sparking. Next you have your power supply. Capacitors are used to reduce power fluctuations in power supplies and to increase the efficiency of power transmission. Now there are certain disadvantages of capacitors as well. The best example is your television sets. Now usually people say that when you switch off the television also, you're not supposed to touch the back part panel of the television, because the capacitors inside stores charges and energy for some time. So if we go and touch the panel, there is a liability for us to get a shock. Okay, that is why you should not touch the panel of the television set, back side of the panel of the television set, even if the switch is off. And one more most practical example is your the capacitors which are used in your ceiling fans. Now suppose, say, I think many of you all would have done it at home or at school. If the fan stops, what we do is we take a scale or just roll the blades. That is, we are just initializing a torque. That is, torque is a rotating force. To rotate that blades, we have to apply a torque. So in the ceiling fan, the initial torque is given by capacitors, which are known as condensers. Okay, that is why if the condenser is faulty, it will not give sufficient initial torque to rotate the blades when the fan is switched on. So these are some practical applications of capacitors. Okay, so that is all with today's lesson. Thank you, children.